Today we're learning all about alkenes. Hey, it's got a pie bond, do you know what I mean? We're gonna learn how to name them and which one of them is most stable. Come on, let's learn. Come on, let's learn. Hey, about alkenes. Hey. That's right. In this video, we are talking about alkenes. Now, we've talked about alkanes before, and alkenes are simply molecules with a carbon-carbon double bond. Remember, this double bond consists of two different types of bonds. We have a pi bond and we have a sigma bond. The molecular formula is CnH2n. Remember, for alkanes, this was CnH2n plus 2. And this makes sense because if I compare butane versus butene, I've essentially just lost one of the protons on each of these carbons. So we're simply missing two hydrogens here. And then this has a double bond equivalence or degrees of unsaturation or unsaturation number. There's a few different ways to label this, but it has a DBE of 1. That's that formula we went over for double bond equivalence. They're also called olefins, and this is an older term you might hear me say, but olefins is a more general term for alkenes. They are more reactive than alkanes because of this pi bond. I want to focus on this pi bond because this is going to affect how we name them. Remember that pi bonds here are made of two p orbitals. So here I have ethylene, and instead of drawing it flat on the piece of paper, I've essentially just rotated it. So the hydrogens are coming towards you and behind the paper here. Here's our hydrogens. And we know that we have a pi bond as well as a sigma bond. Let's review what orbitals make up the sigma bond. Well, this is an sp2 hybridized carbon. So these are sp2 hybridized orbitals for the sigma bonds. Sigma bonds are made from hybridized orbitals. Pi bonds are made from p orbitals. Molecular orbital theory comes back and haunts us again. Now, here I have the p orbitals, and this is the bonding p orbitals, okay? I have them in red and blue, but essentially we need to remember that these p orbitals have to align in order for bonding to occur. These p orbitals inhibit this bond from rotation. So on the right, what I've done is I've tried to rotate this bond. So I've got this double bond to a carbon, and our hydrogen now is coming up and down, and this hydrogen's back, this hydrogen is coming towards you. And notice here how there is no overlap. So if I try to rotate that double bond, the p orbitals no longer align. They're orthogonal to each other. And if they cannot align, there won't be any bond. So you cannot rotate pi bonds. You would be breaking the bond. So you cannot rotate the pi bonds, otherwise you would break the bond. Let's review something that we've talked about with rotation. Now, we've talked a lot about alkanes rotating. And here I have an alkane rotating here at this carbon-carbon bond, and then now I have my methyl coming out towards us if I rotate it the way that I've shown in red. Now, these are sp3 hybridized carbons. There are no p orbitals here that are making bonds. We can rotate these. My first question is, what is the relationship between this compound and this compound? Go ahead and pause the video and see if you can identify that. These are conformers. That is right. These are conformations of each other. I like to remember that because there's an R in conformers. They're conformations. You rotate bonds. You essentially cause from just rotating the bonds. They are the same molecule, though. They're exactly the same. They're just rotated in space differently. Let's take another example. So I'm drawing the same alkane. I'm going to go ahead and make it an alkene. I'm going to remove 2 of the hydrogens. Okay. And then I'm going to compare it to this alkene. Now, this is a butene derivative, and I know that because 1, 2, 3, 4, there are 4 carbons. 4 carbons. And that means that we have a bute base name. And it's an ENE because it's an alkene. Okay, remember alkanes are ANE. So this is ENE. And the alkene part starts on the 2 carbon. Now, I wouldn't call this 3-butene because we always use the lowest number. So this is 2-butene. Now, this is an IUPAC naming, and IUPAC in the 90s decided to come out with a different way to name this. Butene. So if you want to be like a cool old school chemist, call it 2-butene. Everyone will still understand what you're saying. If you want to be a cool 90s organic chemist, call it butene. You can decide who your friend group is based on how they label their molecules and what IUPAC form they use. Anyway, I'm probably going to use the old way. That's how I was taught. So 2-butene. Now, when I look at these 2 molecules, the relationship between them, they're not the same molecule. I can't rotate this alkene to form the alkene where the 2 methyl groups are on the same side. But I could do that for an alkane, right? So these 2 compounds are actually different. They also have different physical properties. Now, these 2 molecules are actually connected the same, so we wouldn't consider them constitutional isomers. This has 4 carbons, and on the 2 and the 3 carbon, there's a methyl on them. See that? 1, 2, 3, 4. On the 2 carbon, we have a methyl, and on the 3 carbon, we have a methyl. What's different is it's this spatial differentiation. So notice that the methyls on the right are nearby each other, and the methyls on the left compound here are further apart or opposite of each other on this alkene. So because we can't rotate them, but they're connected the same, so these 2 are isomers of each other, but in particular, we're going to use a term called diastereomers. In order for a compound to be a diastereomer, it has to have stereogenic centers. Okay, now I'm using big terms. I'm going to star the 2 carbons that are stereogenic centers. And you're going to see that on the purple stars here, these 2 carbons have methyl groups that are in different orientations in space. The methyl groups are further apart on the compound on the left, and they're closer together on the compound on the right. I'm going to write stereogenic centers. We're going to dive into more detail with stereogenic centers. There's more to this story, as well as diastereomers. We can label these alkenes as follows. The one on the left here would be considered a transalkene. The one on the right is going to be labeled a cisalkene. So we have trans and cis, okay? This only applies when both groups you're considering are the same. So in this case, for 2-butene, we have trans 2-butene or cis 2-butene, okay? When you have this cis or trans alkene, they are considered diastereomers of each other. Diastereomers is just the term saying that these 2 alkenes are related, but they have a difference in the stereogenic center. One of the carbons here has a methyl group that's in a different place than the other one, and we can see that visually. This trans-cis naming system only works, though, if the 2 groups are the same, okay? If they're 2 methyl groups or 2 bromines or 2 chlorines. What happens though is if you get a more complicated alkene. So if we were to look at this alkene, trans and cis doesn't work because if you look at it, I have 4 different groups attached here. And then I have a hydrogen. So when I'm looking at this, if I say that it's cis, how do you know which 2 groups are on the same side? So there's a technique that we can use to label which of the groups are higher priority, and it'll help us name them. We're going to use this system when we talk about, in more detail, stereogenic centers. We're going to first focus on alkenes. And notice here, again, that cis and trans work sometimes. The system I'm going to show you works for all alkenes. So whereas sometimes you might want to use cis and trans, totally fine, you can use this next system for all of the alkenes. What we're going to learn is this Kahn-Ingold-Prelog system. I'm going to draw a simple alkene. What we're going to be doing is we're going to be looking at the highest priority groups on either side of the alkene. I'm going to draw a dotted line here to show you which sides we're looking at. So you're really just going to focus on one of the carbons of the alkene, and you're going to decide which group is the higher priority. If both of the higher priority groups are on the same side of the alkene, so in this case they're on the top, this would be considered a Z alkene. And this is coming from the German word zusammen.
Zusammen. Zusammen.
Which means together. This would mean that our lower priority is here. I'm going to put a little versus symbol because the higher priority and lower priority are only looking at either the left or the right side, and we'll go through examples. So this is a Z alkene when the higher priorities are on both the top or the bottom, okay? And then let's look at what happens when we have an alkene where we have a higher priority on the opposite sides. And that would mean that we have our lower priority here. This will make sense in just a minute when we go over examples together. So our higher priority groups here are opposite of each other. This alkene would be labeled an E alkene, and it's from a German word entgegen.
Entgegen, auf Englisch. Opposite. Opposite.
So in these rules that I have listed below, I say that the highest atomic number is the highest priority. Okay. And then if atomic number is the same, use the atomic mass. This only applies if you have an isotope. So for example, if you were to have a deuterium versus a hydrogen, deuterium would win. Let's just do a quick example of that. If I have an alkene that looks like this, here's a deuterium and a deuterium. We know that these are hydrogens. We never draw in hydrogens. We're lazy organic chemists. But if we draw them in, you can see we can draw a dotted line down here. I'm going to circle the highest priority on the right side. Deuterium versus hydrogen. Deuterium wins. On the left side, hydrogen versus deuterium. Deuterium wins. You look at the relationship of the highest priority groups you've circled, and we see that this is lining up with that E alkene. Now, if they're the same, this is when things get a little funky. If we have a tie, when we look at the first atom, we have to then keep looking, and I'll show you how to do that. So again, we're looking at naming at alkenes, and this is because this is another way for us to communicate with other chemists what we have, right? If I just say I have, for example, let's look here. Here's my 2-butene example, right? 1, 2, 3, 4. Bute, 4 carbons, and then ENE because we have an alkene, and it's on the 2 position. Well, but this doesn't tell me the whole story. What kind of 2-butene alkene do I have? Do I have the methyls on the same side or on opposite sides? Okay, these are two different molecules. So as I'm looking at this, what I like to do is I like to just draw my dotted line down the middle of the alkene, and I just look at the right side. I don't know why I always look at the right side first. I'm just going to draw on a hydrogen, and I'm looking at the two atoms that are bound to that carbon there. Okay, so I have a hydrogen, and this one I have a carbon, right? So I'm looking at carbon versus hydrogen. Which one has the higher atomic mass? Carbon. So this group will be our higher priority group. So then I'm going to look on the left side. Same thing. I have a carbon versus a hydrogen. Carbon versus hydrogen. We know that carbon will win. So both of the carbon groups are on the same side. So here's our alkene. They're both on the same side of the alkene. So this would be a Z. It'd be a Z2-butene. And that would be the way that you describe this molecule. Now, I'm just going to throw this in there. The way that I remember Z being on the same side is I just accentuate the S. And I just go, this is on the same side. So that's how I remember it. Same side equals Z alkene. That's how I remember it. You might come up with something else, okay? All right, so that is a Z alkene. And now let's look at our other butene derivative, 3, 4. So we still have a 2-butene, right? And we're just deciding if it's E or Z. And now you know that it is. Now you could also call this a trans 2-butene. That would be fine. But remember, cis and trans doesn't apply to everything. So I like to just use the EZ system because it's still correct. You can call this Z2-butene. You could also call this cis-2-butene, but just remember that cis and trans doesn't apply to everything. The E and Z naming system does. So I would just use that one. Let's do this trans 2-butene. Let's do the priority of either side. Let's start on the right side. I've got a hydrogen versus a carbon. So we know that our carbon will win. All right. And then let's look at the left side. So we have a carbon versus a hydrogen. And in this corner, I'm just kidding. It's like a little fight. It's like carbon's big and it'll win. So these two methyl groups are opposite of each other. And when we look back at our previous slide, we know that this would be an E alkene. So the name for this would be E2-butene. Either is fine for naming. Okay, but E and Z works for all of them. That's why I like using that naming system. Let's do a more complicated one. The one that I showed you earlier doesn't use cis and trans. You absolutely can't use it. It doesn't describe it. You don't know what groups you're talking about when you say cis or trans. So let's do this one together. I'm going to draw my little dotted line. I'm going to look at the right side. I've got a carbon here, and I have a carbon here. So right now, if I do carbon versus carbon, it is tied, okay? Now I need to look at what's bound to those pink carbons. This top example, this top methyl has 3 hydrogens. So the way I write it out is I write a parenthesis and I go H, H, H. Cool. This carbon here, we know it has 2 hydrogens there. They're kind of hiding, right? And it's also bound to another carbon. So this carbon in pink, I'm going to say it's carbon, hydrogen, hydrogen. So out of these two groups, which one wins? We're comparing now kind of a second step because it tied on the carbons. When I'm looking at this, I see that there's a carbon listed for our ethyl group, this bottom group. So the ethyl will win. It is the higher priority group. Let's look at the left side here. So I have a carbon. Okay, and here's our hydrogen. So I say carbon versus hydrogen. Well, that one was easier. We know that carbon will win over hydrogen. So I'm going to circle this group. The two groups here, as I'm looking at my alkene, here's a bond, here's a bond, here's a bond. I'm looking at this double bond. The two groups I'm looking at are on opposite sides. That means we have an E-alkene. Bingo. Okay. Polyethylene, or PE, is one of the most widely produced plastics in the world. It is made from radical or addition polymerization of ethylene as a monomer. You see, alkenes are very important industrial feedstocks for plastics that we use in our everyday lives. Let's move on to some more fun examples. On this slide, I actually have 3 molecules that we're going to first compare wholly. It'll be kind of like a little review. Let's look at these 3 alkenes. So I've got 1, 2, 3, 4, 5. Okay, so this is a pentene derivative, and it's got 6 carbons total. And it's got 1 double bond equivalent. And I know that because it has a pi bond. Let's compare the other ones. Okay, well, 1, 2, 3, 4, 5. That's also a pentene derivative, and it has 6 carbons. Okay. What about this one here? 1, 2, 3, 4, 5. It's also a pentene derivative with 6 carbons. I already knew this. I made the slide, but I'm walking through it because I think that it's important to look and have you hear me walk through how I would do it. So if I were given these 3 compounds and asked to explain what is the relationship between these compounds, this is the first step I would do. I'd first just make sure they have the same molecular formulas. And they do. All right, same molecular formula. What does that tell us? Well, now let's look a little more in detail. How are these compounds connected? Well, if I look at the example on the left and compare it to the example on the right, we'll notice something here. We have these methyls hanging out on the same side of our alkene. However, the one on the right here has a methyl here, and the other methyl is actually on carbon 3. The one here on the left, both methyls are on carbon 4, whereas the one on the right has a methyl on carbon 3 and 4. This means they are connected differently, right? They are connected differently. So if you have 2 molecules that are connected differently, but the same molecular formula, what is it? Go ahead and pause the video and see if you can guess. Constitutional isomers. Bingo. Okay, let's label these 3 alkenes. I'm going to say, so we've got A, B, and C. So I'm going to say A and B are constitutional isomers. What about C? What does C look like? Well, if I look at the carbons here, I see that on carbon 3 and carbon 4, we have those methyl groups, right? But it looks a little different than B. If you notice here, we've rotated this single bond. So between B and C, the only difference is a rotation. Still has the same molecular formula, and they're all connected the same way. It's just rotated differently here on our single bonds. So go ahead and pause the video and ask yourself, what's the relationship between B and C? And if you guessed conformers, you would be correct. That's right. B and C, they're just conformations of each other. Again, I like to remember that because there's an R. So R means there's an R in conformation, so it was rotated differently. Okay, constitutional isomers connected differently. Okay, now that we did a little bit of review, let's label these E and Z. Let's do what we were meant to do with these alkenes in this video. Okay, let's do alkene A to start out with. So we know that we have 1, 2, 3, 4, 5 carbon chain here. That's the longest carbon chain. And we know that we have an ene, pentene derivative. going to start my numbering here. 1, 2, 3, 4, 5, so that I can have 2 pentene, lowest number wins. And when I look at this, I also have another methyl. So I'm going to say that there's a 2-methyl, 2-pentene. Okay, that's cool. But what we really want to do is see if this is E or Z. This is where E or Z doesn't actually apply. Trick question. So in this case, we have these methyl groups on either side. CH3, CH3. So if I were to draw my dotted line and compare the right side, and I say, okay, carbon versus carbon, it ties. And I have H, H, H versus H, H, H. Well, this is also tie. So when you have two groups that are the same, it doesn't matter if you flip those two. You can't get the other diastereomer. There isn't one. So this alkene is simply 2-methyl-2-pentene. It's the only way to put it together to make this compound. When you have two groups the same on the right or the left side, there is no E or Z or trans or cis naming. Let's go to B. It does apply here. So I'm going to draw let me just go ahead and write that out real quick. No E or Z. Okay, now let's move on. B, we have this dotted line here. I'm going to draw my hydrogen in. So I've got H versus this carbon. Which one wins? You got it. The carbon wins. So this group wins on the right side. Now let's look at the left. I have a carbon here and a carbon here. They are officially tied right now. They're tied. So now I have to look at what's bound to that carbon. This carbon has 2 protons and this carbon has 3 protons. And there's also a carbon here. So let's label this. So this carbon up top, that's in pink, has a carbon, hydrogen, and hydrogen. The carbon on the bottom has a hydrogen, hydrogen, hydrogen. Which one wins? Well, the one that has the carbon in it, right? So this ethyl group wins over the methyl. So we circled that as our higher priority. When I look at my alkene, in green that I'm drawing, those two groups are opposite of each other. So this would be considered an E alkene. So this would be E, (3-methyl) 2-pentene. Oh, where did I get the 3, right? If I count these carbons out, 1, 2, 3, that's where I get the extra methyl there on that 3 carbon. So E3-methyl-2-pentene. Okay, same thing for this one. 1, 2, 3. Let's do C together. 4, 5. So this is again a 3-methyl 2-pentene. Now, we already decided that these two, B and C, were conformers of each other because I just rotated that single bond. So if you're on an exam, you don't have to then go back through and find out if it's E or Z because it's just a conformation. So it's still going to be an E alkene. You can prove it to yourself. Just pause the video and walk through the same formula we did for E or Z and determining the higher priority groups on either side. Let's go on to some more advanced structures. Structures that have lots of, I call this structures that have lots of spinach, okay? It's just got lots of fluff going on the compound. And if you're simply asked for if this alkene is E or Z, you're just going to hone in on the alkene and you're going to hone in on the 2 carbons of the alkene and what's bound to those carbons. Let's look at this top one together. I'm going to draw my dotted line down this alkene. Okay, so I cut it in half there. We're going to look at the right side first. I always start on the right side. I don't know why, but we're going to start on the right side. When I look at the carbon that I have a blue dot on, I see that I have a carbon. It's bound to a carbon, and it's also bound to another carbon. So right now, these are tied. Carbon versus carbon, tied. Now you move to what is bound to that pink carbon. All right, So this pink carbon has an oxygen, but it has 2 bonds to that oxygen. So I'm going to write O, comma, O, because there's 2 bonds to it. And that pink carbon is also bound to a carbon here. So OOC. All right. This pink carbon on the bottom is bound to 3 carbons here. Carbon, carbon, carbon. When I compare these two, the oxygen wins because of its atomic mass. So this group is a higher priority. Let's look at the left side. I have a hydrogen here, okay, and this is the carbon. So I'm going to go carbon versus hydrogen. Now, we don't care so much about what else is bound to the carbon because it already won. Carbon versus hydrogen, this top group won already for the atomic mass of carbon being higher. In green, I'm going to draw on my alkene again just to confirm to myself which side these 2 higher priority groups are on. My alkene in green shows that the 2 lines are on the same side. The same side. So this would be a Z alkene. Let's do the example on the bottom here. I'm going to draw my dotted line through the alkene. Let's look at the right side. I don't know. I always just look at the right side. I don't know. This alkene has a carbon and a carbon. Right now they are tied. They are tied right now. That means we need to look at what else is bound to those pink carbons. So the carbon on the top, I have a hydrogen, and there's also a carbon here. The carbon on the bottom is bound to a hydrogen. Don't forget there's a hydrogen there. Remember, every carbon has 4 bonds. There's a hydrogen, carbon, carbon. So hydrogen, carbon, carbon, okay? And this one is a hydrogen, hydrogen, carbon. Which one wins? The bottom one. There are 2 carbons here listed versus just 1. So this tert-butyl group is a higher priority than the ethyl group, okay? Tert-butyl is higher than ethyl. Now notice you could memorize that. You could memorize that tert-butyl is a higher priority than an ethyl group, but that means you'd have to memorize like all of the relationships, okay? You'd have to then memorize that tert-butyl is also higher than isopropyl, and it would just become too involved. So what I like to do is I like to teach you the method, and you're going to develop an intuition as you keep practicing. I don't expect you to be able to look at something and know right off the top of your head that that's an E or an Z alkene. That comes after a lot of practice, For now, I just want you to be able to do the method so that you can actually answer to any alkene. You can figure that out for any alkene that's given to you, which I think is a better skill to have than just memorizing random facts, waking up from a nightmare of tert-butyl is higher priority than ethyl. I don't want that to happen. Let's do the next one. Okay, carbon on the left side, carbon versus carbon. We're tied. It doesn't look like it, but we're tied right now. Now we need to look at what it's bound to. The carbon on the top here in this phenyl ring has a carbon and another carbon. This carbon here is just singly bound, okay? But this carbon on right here has 2 bonds to it. So it's carbon, carbon, carbon. Okay, the one on the bottom here is a methyl group. So this carbon is bound to H. H, H. Well, that one was pretty simple. H, H, H. You might not have had to write all that out, but I wanted to do this just in case you did. Totally cool to do it. I still do this sometimes. All right, so the top one wins because it has 3 carbons there on that second round. After it tied the second round, the phenyl ring definitely beat the methyl group. But again, you didn't have to memorize that a phenyl ring is a higher priority than a methyl. But eventually, you'll just know that off the top of your head. Let's confirm which side these groups are on when we draw in our alkene in this green. Cool. Look at those 2 bonds. They are opposite of each other. That means that this is an E alkene. Entgegen. Did I sound German? Probably not. Okay, E alkene. So cool. So now we know how to name stuff. And so that's it for this video. In this video, we talked about alkenes. We talked about how to name them. We looked at the cis and trans naming. That doesn't apply to all of them. So then we looked at the Kahn-Ingold-Prelog system, where we can identify which substituents are higher priority. Now that system we're going to use again and again. So it's useful for us to practice it on alkenes where we only have two things we're looking at on each side. So in this video, we learn how to label things E or Z. Don't forget, Z is the same side, on the same side of the alkene, and E, they're further apart and opposite. So that's it for this video about alkenes, and I will see you in the next video.